Fine, we hear you.
It is a pleasure for me to be here and speak to you, distinguished audience, on my distinguished friend. So the title of my talk is The Remarkable Journey of the Isoperimetric Problem, a completion of Euler's approach. So the isoperimetric problem is one of the most famous problems of all time. And Euler was the first person to try to solve it. And we're going to talk about Euler's approach. And Euler did not finish his approach. And what we're going to do is try to finish it. So let's go. Now, Leticia, this doesn't. Just a minute. Okay, so this talk is dedicated to the memory of Roland Lewinsky. Now, he was a great mathematician, as you heard, but he was a better friend. He was actually my best friend for many, many, many years. So I feel very honored and also sad speaking in memory of Roland Lewinsky, but he was a great mathematician. Here's an outline of my talk. I'm going to talk preliminaries. Then I'm going to tell you what Euler did with respect to the isoperimetric problem. And then we're going to finish what Euler didn't finish, and that's our contribution. So we go preliminaries, what Euler did with respect to the problem, and then our contribution. I've been working on this problem for many, many, many years, not full time, but many, many years trying to finish what Euler did. All right. So the preliminaries. The isoperimetric problem is determined from all simple closed planar curves of the same perimeter, the one that encloses the greatest area. Okay, that's the isoperimetric problem, and everybody knows that problem. Okay, the problem is highly visible because there's many stories about it. In Roman mythology, we had the Aeneid written by Virgil, and in that story, in Roman mythology, Queen Dido, her life is in danger, and she flees her homeland with wealth and a group of people, and she finds new land and bargains with the local king for a piece of land that she can mark out with the hide of a bull. The Dido trick is to cut the hide into as many thin strips as possible, to form a long cord, and using the seashore as one edge, lay out the cord in the form of a semicircle in order to maximize area. So here is an engraving in the German museum that appeared about 1630. And so what you see is there's Dido in front speaking, and she's telling her workers to cut the hide of the bull into long, thin strips to enclose a maximal domain. So this problem and the isoperimetric problem and Queen Dido is very, very well known. Okay, everybody knows it. Okay, so here's an example of the Dido principle in action. So this is a map of Cologne. Okay, and this is medieval Cologne. Then here's a map of medieval Paris. And you see that basically there's the river, and see how it's in a form of a semicircle. And so we actually see it on purpose in action. All right. Okay. So the isoperimetric problem has been the most impactful mathematical problem of all time. That's what I'm saying. It has been the most impactful. Euler constructed a multiplier theory. So what we know as Lagrange multiplier theory, Euler actually built multiplier to try to solve the isoperimetric problem. Weierstrass first introduced parametric representation of a curve or a function to solve this problem. So there's a lot of things that came from this problem. Okay. Now, what did Euler do or not do? Many people criticize Euler. They say he did something wrong, he did something incomplete, he did this, he did this. And his work was not translated for a long time. So people didn't know. So what we're going to do is first see what did Euler do, okay? So Euler considered what we call the incomplete isoperimetric problem, okay? So look, maximize area. See, you all recognize area up on top, subject to arc length. So we see the integral for the area, and then we see the arc length integral, and then we have the boundary conditions that it vanishes at the curve vanishes at minus a and a. So that's the isoperimetric problem. And what he considered was for a fixed a. So in other words, a is the base interval. And so Euler considered this problem for fixed a. And a should be a variable, but Euler didn't think of it that way at all, okay? So we call this problem incomplete because both y and a should be variables, but only y. So this is what Euler considered the incomplete isoperimetric problem, okay? Now, Euler's contribution to the isoperimetric problem. He constructed the Euler multiplier rule auxiliary problem. Now look at this. He took the arc length constraint and he put it with a multiplier into the objective function. So Euler considered maximizing j of y, which is the interval, and then you have the area, and then you have a multiplier, and then you have the arc length. So he was the very first one to ever consider a multiplier rule. That's to his credit. He showed that a solution of the incomplete isoperimetric problem must satisfy the Euler-Lagrange equation for the auxiliary problem, and therefore must be arcs of the lambda parametric family of circles. So see that line right there, y of x looks like that. What Euler did is, using multiplier theory, he showed that the solution to the isoperimetric problem must be of that form, okay? So, and the radius parameter lambda is determined from the arc length condition that is given. So this is what Euler did. He took the problem, he formulated it as a multiplier rule. Then he said that the necessary conditions are that it looks like this lambda parametric family of circles. This is exactly what Euler did, okay? Now, since if you reverse and interchange y and the square root of 1 plus y prime, you get the same thing, except for maybe the multiplier being a little bit different. Euler observed that the two problems are equivalent, determined from all simple closed plane curves of the same perimeter, the one that encloses the greatest area, or determined from all simple closed planar curves that enclose the same area, the one that has the smallest perimeter, okay? So you could either put the area as a constraint, or you can put the perimeter as a constraint, okay? So that's called Euler's principle of reciprocity, okay? And it follows, and it became very important, but Euler observed it first, okay? This is in 1744, okay? Now, observe that the semicircle, the first equation is the semicircle, okay? So it satisfies Euler's necessary condition. It has the form of the lambda parameter family of curves. So the semicircle is an example of one of the curves in Euler's family of curves, okay? However, one of the things that is wrong is, while the semicircle satisfies is in that family, here's a very delicate point that people seem to miss, okay? So an obstacle in Euler's path or road, while the semicircle does satisfy Euler's necessary condition, it's not in the domain of definition of the optimization problem. It does not satisfy the arc length constraint. So look, what I'm telling you is that the semicircle is has a fixed arc length, and it's very nice, but you can't get it as a Riemann integral. Here, consider the semicircle. There it is. For the semicircle curve, the arc length integral right there does not exist as a Riemann integral. So if you differentiate, you'll see that the derivative is not bounded, okay? So see, y prime equal minus x over square root of a squared minus x. As x gets closer to a, that term becomes unbounded. So the integral is not bounded, hence it cannot be Riemann integrable. So it is an interesting situation that we're facing right now, is this. No, the situation we're facing is that while the semicircle satisfies a necessary condition, it's not in the domain of the optimization problem. It does not have an arc length, which can be represented as an arc length integral. So there's a problem there, and nobody seems to pick that up. So that's a very subtle, but a very important question, that the semicircle is not in the domain of the isoperimetric problem that Euler considered, okay? So what did Euler do? Euler's 1744 approach to the isoperimetric. He showed solutions to the isoperimetric problem in incomplete form are necessarily circular arcs. That's nice. He said nothing about the semicircle. He said nothing about the complete isoperimetric problem, i.e. where the variable, the base parameter A is also a variable, and he gave no restrictions on A. The majority of the text on the calculus of variations follow Euler's presentation of the isoperimetric problem. Hence, students cannot find a demonstration that the semicircle satisfies even necessary conditions for either the incomplete or the complete isoperimetric problem. It is interesting how many textbooks avoid this shortcoming. So there's a subtle gap here. There's a subtle problem, is that it doesn't fit right, and textbooks, you know, mathematicians are very tight in their definitions and stuff, but yet they miss this point that the semicircle does not, it does satisfy Euler's necessary condition, but it is not in the domain of definition of the problem. Remember that. That's the important point we're saying, is that the semicircle is not in the domain of the definition of the isoperimetric problem. So still put, why is it not in the domain? Because you can't find its arc length by an arc length integral, okay? It doesn't exist as a Riemann integral. Okay, now, Euler's naivete considering the Euler-Lagrange equation. Hermann Goldstein says, it is interesting that Euler did not completely understand the fact that the satisfaction of the Euler-Lagrange equation is a necessary condition, but not a sufficient one. Now, Euler's genius. Kara Theodori, who edited Euler's great works of 1744, said, Euler's multiplier rule is an achievement of the first class and a major accomplishment that even an Euler did not achieve very often. So he said that is an incredible. So Euler came up with the multiplier rule, okay? Now Euler's generosity. Euler was so impressed with 19-year-old Lagrange's derivation of the multiplier rule using variations that he dropped his own methods, promoted those of Lagrange, named the subject the calculus of variation, and called multiplier theory Lagrange multiplier theory. Indeed, today the Euler auxiliary function, which we just looked at, and it's given above, is called the Lagrangian. How fair can that be? Okay, so Euler discovered this wonderful auxiliary equation with a multiplier, but he called it the Lagrangian. So how fair can it be? Does Euler have the right to take his great accomplishment and call it the Lagrangian, okay? Most people will say, or some of my students say, yes, he has the right because it was his equation. And I say, no, he does not have the right, because once it was etched in the annals of history. So once that equation came out, it was tied to Euler, and you cannot change history. So you can't change history. So it should be Euler's equation. And for a while it was Euler's equation. But then after a while, they started calling it Lagrange's equation and Lagrange multiplier rule. So Lagrange multiplier theory should be called Euler multiplier theory, but it's not, okay? So Chiara Theodori in 1957, editor of Euler's work, wrote, Weierstrass succeeded in removing many of the difficulties that were contained in the investigation of Euler, Lagrange, Legendre, and Jacobi by insisting that first the class of curves in which the minimizing curve is sought be rigorously defined. Euler's treatment of the isoperimetric problem is a prime example of this lack of rigor. So Chiara Theodori said that all these great, wonderful mathematicians are mathematical pioneers. They didn't define the class they were working in. And Euler did not define the class that we were working in. And that's how they made so many mistakes. So Chiara Theodori points out that you have to define the proper class. Euler did not define the proper class, okay? So that's the background. Now we're going to try to complete. See, Euler gave us a necessary condition. He said that the solution of the isoperimetric problem has to look like one of those, be a member of this family of circular arcs. And he stopped there. In fact, he didn't go any further. He gave us this necessary condition, and actually he said nothing about the semicircle. Okay, so the first thing we have to do, according to Chiara Theodori, is give a definition of the proper class of functions. So I'm going to call this the Euler class of curves that we're going to work in, okay? And so we have the boundary conditions that y, and the base parameter is a, y minus a, y base 0. We want the curve to be continuous. We want it to be differentiable, except possibly at a countable subset of minus a and a. Notice that the semicircle is not differentiable at the endpoints. The slope is infinite. So it's differentiable everywhere except at minus a and a. The curve y is rectifiable. That means it has an arc length, a well-defined arc length. And the arc length can be obtained from the formula, and that's the improper integral for the arc length. See, you move away, you put minus epsilon, and then you let epsilon go to 0. So the fact is that we're going to replace in the regular thing is the arc length integral with the improper arc length integral. So this is the Euler class of functions that we're going to win. And we're going to try to, here's what we want to do. First, we want to show that the semicircle is in this class. And then we want to show, excuse me, that the semicircle maximizes, solves the isoperimetric class, the isoperimetric problem over this class. That's what we want to do. So look, first thing we did is we defined a new class of function. Now, the first thing we have to show is that the semicircle is in our class. That means that, well, the Riemann, so the arc length integral does not exist for the semicircle. Maybe the improper integral does exist. That's what we have to show, okay? So look, we're not going to read this, but the semicircle is in the Euler class. So simple high school geometry shows you that the improper arc length integral is valid, and that the semicircle you can get the arc length of the semicircle from the improper arc length integral, and it's simple. We're not going to go through that. All this is important to say that the semicircle is in the Euler class that we just defined, okay? So now we're going to look at the complete isoperimetric problem. That means, what does complete mean? That we're going to consider both the base parameter and the curve y as variables, okay? So incomplete was what Euler did is he just tried to maximize over y, the curve, and he didn't mess with the base parameter. So they're really both variables. So you have to say, okay, let's go off and be very strong and real macho, and let's try to do both variables, okay? People do not do that in the literature, okay? This is our contribution. So we state the problem that maximize the area subject to the arc length and have both A and Y, the base parameter and the curve, as variables, okay? So we take that two variable problem and we state it as a bi-level mathematical model of the complete isoperimetric problem, okay? So the first level one, so look, level two of the bi-level problem is to, for a fixed A, find the curve that gives the largest area. That's the second problem. For a fixed A, find the curve Y that maximizes the area. Then the first level problem is, now that you have those, is take the Y's that you just determined in the second level problem and find out which one gives you the maximum area as a function of A. So in the bottom problem, Y is the variable. In the top problem, A is the variable. So we've separated it. Hopefully we can solve the second level problem and the first level problem. And if we have a complete proof of the that the semicircle solves the isoperimetric problem. Okay. That's what we're going to try to do. Solve those two problems. Okay. And that's what Euler should have done. Okay, so look, here's an observation. From this picture, we can determine that the Euler family of curves that Euler came up with requires A to, and with a given arc length, say for fixed arc length L, the choice of lambda, which is the radius of the curve, of the circle, of the circle that gives a circular arc, determines the base parameter A. The choice of lambda A leads to A equals L over pi, while the choice of lambda equal to infinity leads to A equal L over 2. So A has to be in the Euler family of curves, A has to be between L over pi and L over 2. So that's the interval that A can be to be a member of the Euler family, okay? So the solution of the level 2 problem. So here's what we're going to do. Say, consider the incomplete isoperimetric problem, the level 2 problem with arc length L and base interval parameter A between, we just showed that it has to be between L over pi and L over 2. Now, then there exists a radius parameter lambda star, so that the Euler family circular arc, that one right there, has the length that was given, L, and is the unique solution of the incomplete isoperimetric problem. So we're saying, look, there is a choice of lambda that will solve the level 2 problem, okay? See, Euler said that it's a necessary condition to be a member of that family to solve the level 2 problem. But we're saying it's sufficient. So we're not, while Euler said necessary, we're saying, no, there's more. It's sufficient. So that choice for the given L, that choice of lambda star will lead us to a curve. And we call that curve Y star, okay? So let's call it Y star. Now, we want to show that that Y star solves the level 2 problem. So here's what we're going to do. We'll consider Euler's epsilon perturbed auxiliary function. We'll give it a call the Lagrangian, with choice of multiplier equal to minus lambda star, or lambda star is greater than 0, is the radius of the circle that determines the circular arc. So look what we're going to do. We're going to work with the Lagrangian, okay? And we're going to define it on the Euler class of functions. And if we And here's what we're going to do. We're going to move away from A and minus A by epsilon. Then everything is well defined. So we're going to try to maximize the Lagrangian, because in optimization, if you can maximize the Lagrangian, then you solve the maximization problem. So we're going to mess with the Lagrangian. There it is right there. It has a 2, okay? And let me do this. So condition D of the definition of the Euler class of function. Here's what our condition D was. I'm repeating it so that you remember. The curve Y is rectifiable. That means that it has well-defined arc length. And the arc length can be obtained from the formula, the improper integral, okay? So our class has that the arc length can be obtained by the improper arc length integral, okay? And that means that as epsilon goes to 0, the Lagrangian is going to exist, and we're going to have that L naught of Y, that's mean epsilon equals 0, is going to be the limit of Lagrangian and epsilon, okay? So as I said earlier, recall from optimization theory, if an element maximizes the Lagrangian, then it will solve the maximization problem. So we will try to maximize the Lagrangian, okay? And this is very, very tricky, okay? So in order to do this, we'll turn to Taylor's theorem. So look, take any other Y in the Euler class. Not Y star is the one that we have just picked that gives us the correct arc length. And we're going to define phi of t epsilon as that function right there, okay? Now, what we want to show is that phi of 0, okay, is maximized. So this is, you get the idea, but the details are hard to follow. But here's what we want to show: that the Lagrangian for epsilon equal to 0 for an arbitrary Y in the Euler class, which we can write as phi 0 of 1, is less than phi 0 of 0, because that's the one we have for our Y star, and that's equal to the Lagrangian of our fixed Y. That's what we want to show. So how do we do that? We turn to Taylor's theorem. Okay? And I'm not going to go through all this, but look, we have this phi function, and we turn to Taylor's theorem. And we take the first derivative and the second derivative. And Taylor's theorem with remainder tells us that, look, there's Taylor's theorem. And it has a remainder. The second derivative has a theta epsilon in it, which theta epsilon is a parameter between 0 and 1, okay? So that's what we want to do. We want to show that we can use Taylor's theorem to accomplish what we want, okay? Now here's an interesting point, that this is Taylor's theorem with remainder. So, so theta epsilon is something between 0 and 1, and it changes. And so a lot of people who read this said, oh no, you'll never do anything because theta epsilon, you don't know, it's not, you don't have any way to get a hold of it. It's just some parameter between 0 and 1, okay? So if we start to play with this formula, since theta epsilon is bounded between 0 and 1, it has a subsequence which converges. So we therefore have that the second derivative, see the second derivative up there on top, is that will converge with our theta epsilon. Okay. All right. Letting epsilon go to 0 in 4 and using our Euler class D condition, that means that the improper integral exists, okay? We end up, just from that phi, that area of Y minus lambda star length of Y is less than area of Y star. That's the one that we picked, Y star. Yeah. So if the two curves have the same length, then you take the lambda star length out of it, and you get that area of Y is less than area of Y star. So conclusion, we have, so the conclusion is that Y star uniquely solves the extended incomplete isoperimetric problem for A contained in that R interval. So we have solved the level 2 problem for A contained in the interval L pi over L over 2, okay? So it took me a long time to think of this approach, but notice that it really doesn't use powerful tools. It just uses, what's the key ingredient? Taylor's theorem with remainder. Taylor's theorem with remainder, okay? So the pieces fit together so remarkably well. In mathematics, when pieces fit together really well, you know it's right. It has to be right when they're so beautiful. So all these integrals, when I started working with them, here, the second and the first, everything was so beautiful. It was just absolutely beautiful, okay? Now, here's a question, okay? Could Euler have made our observation at the time of 1744 writing? Could Euler have done what we just did? See, what did we do? We took what Euler started, and then we completed it. Well, not yet, not completely. So we asked the question, could Euler have made our observation at the time of his 1744 writing? The foundation of our observation is Taylor's theorem with remainder. You know, in calculus, we have Taylor's theorem. And Taylor's theorem, okay. The literature tells us that Taylor published his theorem in 1715. So Euler most likely was aware of Taylor's theorem in 1744. However, the rub is that Taylor's theorem with remainder was not known at that time. It is somewhat ironic that the form of the remainder that we use in our proof is credited to Lagrange in 1797 and is actually referred to today as the Lagrange form of the remainder. So Euler would not have been in good position to make our observation because the form of the Taylor theorem that we wanted was not there at that time. So he couldn't have done it, okay? Lagrange could have made the proof because he was familiar with the form of Taylor's theorem that we use. Indeed, it's due to him. While this hypothesized proof would have been made 50 years after Euler, it would still have been some 80 years before Weierstrass. Weierstrass is the first one to give the proof of the isoperimetric problem. But Lagrange did not consider the isoperimetric problem. He could have solved it. Lagrange could have, but he didn't. And Euler didn't have the tool to do it the way we did it. Okay. So we have solved the level 2 problem. So now we move on to the level 1 problem. Okay. And the level 1 problem of the bi-level problem and the solution of the isoperimetric theorem. For a given arc length L, the semicircle, that's the semicircle right there, see it? And the base interval is X is between L pi and minus L pi. You can just figure what that base parameter has to be for the semicircle. Now we can claim that it uniquely solves the bi-level complete isoperimetric problem for base parameter A containing that interval. So that's the interval that Euler showed as necessary conditions, that circular arcs, for him to be the necessary condition circular arc, the base parameter has to be in that interval right there. Now Euler didn't say that, but we just determined that. So let's see what we see, okay? So look, we're going to take a picture, draw a graph, a graphical interpretation of the circular arcs with arc length L, okay? We're given arc length L and varying radius parameter lambda and varying base parameter A contained in the Euler family of circles as shown in figure 1 below. So what we've done is we looked at the Euler family of curves and we start to look at, as lambda varies, we get a different arc of the circle and we just draw a picture. We draw a picture, okay? And just looking from the picture, it tells you that the semicircle is going to give you the biggest area. That's what the little picture said. But just to go a little further and not no, so we use insight from the picture. And we actually now just do some high school trigonometry. For fixed L and A varying in the interval between L pi and L over 2, the area of the crosshatch secant region in figure 1, and the one I had before, as a function of the radius parameter lambda, that's what the area is, okay? It's L pi over 2 minus L squared 2. So this is just high school trigonometry. So now if you look at, that's the area formula. So you do a differentiation and you find out that for the lambda star, which is L over pi, that gives you the semicircle. We have that the derivative of this area function is 0 and the second derivative is negative. So that means that lambda star, that means a semicircle, is a maximizer of the function. Okay, so observe that lambda star equal L over pi can only happen for the semicircle, okay? So we have shown that as long as you're within that interval of L over pi, comma, L over 2, the semicircle is good, okay? And it's gonna do the best job. So we're not completely through, okay? Wait, we are not through, okay? Look, see this curve? So if A is between L over pi and L over 2, okay, then we're okay. Now, we can't have A less than L over pi because then the necessary condition wouldn't hold. That means that Euler's necessary condition wouldn't work. So we know that that we won't have a solution to the problem if A, the base parameter, is less than L over pi. So for example, here's a curve, look, and A is less than L over pi in this curve, and the curve has arc length L, and the semicircle has arc length L, and you don't know, so we have to show that that curve cannot have area greater than a semicircle. We have to show that, okay? No one in the literature has ever thought of that. And I had a proof and I gave it to my class. I have a graduate class. And an undergraduate from Rice named Jimmy, he's Chinese. He found an error in my proof. So I try to prove it, that we can't have a curve with base parameter less than L over pi that has a greater area for the given arc length. And so I couldn't prove it. And so Jimmy, the undergraduate student, proved it. And I want to show you now what Jimmy did. Okay. So here's the theorem. In the extended complete isoperimetric problem, where we have A greater than 0, it is sufficient to restrict the variable to the interval. So what I'm saying is you don't need to think outside the interval minus L over pi and L over pi, okay? Hence, for a given R length L, the semicircle uniquely solves the bi-level complete isoperimetric problem with A greater than 0, okay? So here, we start to look. A greater than L over pi implies there are no feasible curves, while A equals L over pi implies that the only feasible curve is identical, y identically 0, the x-axis. Now, if A is less than L over pi, then the following picture shows that any curve y with arc length L cannot have greater area than the semicircle. So look at this picture. This is a beautiful picture, a beautiful picture. So we're going to look at it, okay? So here's what you do. You take the curve. See the curve out there? It's in dark gray, okay? And there's a semicircle with the circle. Now, A is less than L over pi, and the semicircle and the curve have the same arc length L. But you want to show that the dark area which is under the curve, is less than the area under the semicircle. That's what you want to do. So here's what, so look, it says, the proof of this theorem is due to Rice undergraduate Jimmy Zhang, and was produced while he was a student in my graduate optimization class. He's one of the best students I've ever taught. So look, you realize that what he did is he took those red dots and he took the curve and he flipped it, okay? And then he took the curve and he flipped it over the x-axis. So if you look at the curve that see the red line. So then he went to the curve and found the maximum. And then when he found the maximum, he took this and he flipped the curve, the red dot. So he took the left red dot and put it where the right one is. Then he flipped it over the x-axis. Now here's the clever thing. Here's really the clever thing. See the red line? Think of the red line as the x-axis, okay? Then the area under the flipped curve, okay, which you see is all the horizontal hatched line, and the area under the original curve are the same. Just convince yourself of that the area of the curve that we have flipped that's above the red line is the same as the area above the x-axis of the original curve. That's it, okay? Now look, observe this. If the distance of the line D primed is less than 2L over pi, then that means it fits inside the semicircle. And so the semicircle will have a greater area because it fits inside. Now, if the distance between D and D prime is greater than 2L over pi, okay, see the way that the picture is? In that case, then the previous theorem, see, the previous theorem had for the base parameter to be between L over pi and L over 2. So if we have two situations. So if the distance of that line, if the length of the line D prime is less than 2L pi, then we fit inside the semicircle and we're through. If it's greater, then it applies, the previous theorem applies. So it works. So this flip, which I call the Jimmy flip, okay, is what completed my theorem. And I went a long time playing with this stuff, not full time, but I really want to acknowledge students, how wonderful role that they play and how they can help you in your work. And so all my life, I had students help me with my work. And when I teach a class, they help me with the writing of the book that I'm writing and stuff. So anyway, you have to believe that that picture says 1,000 words. They say a picture says 1,000 words. Well, this one certainly says 1,000,000 words. Corollary, the circle solves the isoperimetric problem. So, okay, so that's thank you. So what did we do? We redeemed Euler. We followed the approach that Euler started, but he didn't finish. And nobody else finished it. They left it and they would go in other directions. They would either use geometry or they would use parametric representation. But for many years now, I've been playing with trying to finish Euler's approach to the isoperimetric problem. And hopefully, we've made Euler happy, okay? Hopefully, we made Euler in his grave happy, okay? That's what I hope. So I thank you.
Beautiful talk. Then it's time for questions. ¿Alguien tiene alguna pregunta?
Hay preguntas. it's hard, you know.
I have a question for you, Richard. It's not a technical one, but I think that is important. I'm very impressive about your results because they show that you have done a very deep analysis of this apparently simple problem. So I believe that you have studied this problem deeply from a long, long time.
Right. That's right. I have. And it, and it all started this way. I thought I had a really simple proof and I taught it to my class. And then when you teach something to a class, you know that if it's right or wrong. Hey, you may write something, you say, oh, that's beautiful. Then you teach it and you find out that's a mistake. So I kept teaching this and I found a mistake and a mistake. And finally, the last time I thought, I even gave an invited talk on the subject, and I didn't realize that I had this last mistake in it. And then I gave it to my class. And the student, as I said, he found the mistake. But there's more to it. Not only did the student find the mistake, he gave me the fix. I mean, he told me how to fix it. And so I'm very proud to say that there are many students who I've taught who have far more, let's say, innate talent than I have. And that makes me proud. Okay, that makes me proud. I don't want to say that, oh no, I'm more talented than all the students. That's not true. What I want to say is I have taught students with great potential that will go on and hopefully do great things. Okay. So it's an ending. It's a good story. I mean, it's a good story. And yeah, I spent a lot of time on it. I spent about 10 years.
All right. All right. Well, vamos a agradecerle de nuevo. Let's thank again. Thank you very much, Richard. I hope that we can meet you in person in the future. We are very in depth with you. Thank you very much.
Well, you know, look, en el fondo del corazón soy mexicano, okay? Mi mamá y mi papá nacieron en México, okay? So yo sé que soy mexicano, pero nací aquí en los Estados Unidos, okay? So yo estoy muy orgulloso que soy mexicano, okay? Mexicano-americano, okay? Y esa cosa sí. Y me gusta México mucho, mucho, mucho. He visitado muchos lugares en México, mucho, pero estoy aquí. So, gracias para ustedes porque yo ahorita por eso que, por un momento estoy en México, por un momento estoy en México.
We are very happy of having had you here. So thank you very much again. And for sure, we are going to invite you in the future. Thank you.
Okay.
Pues, gracias a todos. Pues vamos a comer. Están invitados para la sesión de Roland mañana.